All right, everybody, welcome back from the break. The speaker who's about to approach the stand is Glenn Warner. Glenn Warner is a professor in the Natural Resources and the Environment Department at the University of Connecticut. His principal areas of interest are in water resources, with a specialty in soil and water management and landscapes. His research includes groundwater surface, water interactions, water and chemical movement in soils, and modeling dynamic processes and interactions in ecosystems. Let's welcome Glenn Warner.
Thank you, Mike. Good afternoon. Okay. Well, I'm bringing you back to the East Coast here, but we're going to maintain the theme that we have water conflicts here, but at a much localized scale. I'm going to talk about a study that I was heavily involved with, involving the University of Connecticut's water system in Storrs campus in Mansfield, Connecticut, only about 40 miles from here. Just to give you a little overview of what I want to talk about, first I want to talk about the university's water system and water use to set the stage for this study, and then about the specific need, objectives, and background of the Fenton River study, description of the Fenton River and its well field, field investigations, results of severe drought in 2005, which opened not only our eyes but the eyes of many people as to the impact that could occur in these fairly small river systems from groundwater pumping. And then I want to go into that study in a little more detail as far as the groundwater investigations, the fisheries investigations, some recommendations from the study, and then go back and look at what's happened since 2005 to see what the university has done, because they've done some very good things since that time. And the university system is somewhat unique. It's owned by the university. Both the water supply and the wastewater treatment system is a self-contained or owned by the university near campus or on campus. And the water supply consists of two groundwater well fields, one on the Willimantic River west of campus, one on the Fenton River or aquifer deposits near the Fenton River east of campus. And I'm going to only talk about the Fenton River. There is a current study going on for the Willimantic River. The water serves student dorms, offices, labs, etc. on campus, as well as some residential areas in the Storrs campus area, mostly associated with the university. I might add that there's no cost for the water for most of the university. Unlike a small city where you would have meters and people would be charged for the water, we don't get charged in a dorm or in a department building for that water. So it's unique in that regard also. The people who are say some residents around there, I'm not quite sure. I think they pay like an annual fee, but it's traditionally in the past was not metered. We are undergoing a large metering campaign to put meters on many of the uses around campus. The water mains from the two groundwater well fields bring water to campus and is stored in two sources. One is called the towers, and it's the elevated system, holds around, as I recall, 800,000 gallons of water. The other is a large underground, relatively large underground reservoir, and holds 5.4 million gallons. It sounds like an awful lot of water, but our average daily demand historically has been around 1.2 million gallons per day. Peak demand about 1.6 million gallons per day. And if you look at those numbers, you say, yeah, we have 3 or 4 days of water stored in our reservoirs where we would not have to pump, or if we could not pump for some reason. It's really not the case. Much of that water has to remain in those reservoirs for pressure purposes, say in the elevated towers, or with amount of water needed for fire suppression. So even though it looks like we might have about 3 days of supply, it's really not the case. We have to pump every day, continually. In fact, the wells on the Mansfield campus, or Mansfield, the Willimantic aquifer, pump continually. Okay, the peak demand is in August and September. This too is somewhat unique, and I'll go into that in a minute. If we look at the historic use of water in Storrs by the university, we have, there's a jump here, but we were going down as far as population here and in our average daily demand of water use until about 1997, in which we had a large campaign for improving facilities on campus, and it helped that we started winning some basketball tournaments. But we have an increasing population here from about 1997 through present until 2006 at least. During that time, although the trend in water use did not go up at the same rate, it did go up somewhat. And then there was a jump in here from 2003, 2005 era. Since 2005, it's actually decreased, even though the population up here has stayed about the same. And that's because of some conservation measures that the university has undertaken. I'll try to have time to come back to this later, but I want to give you that trend. It's not quite the exponential growth that Peter talked about, nor the exponential increase in water use that goes along with that. These are not quite parallel, but there is some increase in there. If we look at the seasonal aspects of this, we have two times when we really use water. One in the spring semester, one in the fall semester. Summer, we don't use a lot of water. Students leave in May. It dramatically drops as far as water use. They come back in late August. It jumps. September is our peak month. And the other thing I'd point out here while I have this up here, the blue is 2005. We started some reduction measures in 2005. 2006, 2007 have been going down for the most part in each month, so it shows that reduction there. And drastically here in September, and peaks really have an important role to play here, because that's what you build your system around, is the peak rates. Okay? If we couple that with some analysis of the frequency of flow and the variation of flow in our river systems, we find that that peak demand period coincides right in here with one of the lowest probabilities of having high flow in our rivers during that late August, early September period. Of course, this whole thing is driven by our hydrologic cycle, low ET, high rainfall, high ET, moderate rainfall, then in the fall low ET again, so we get recharge and more flow in our rivers. But we have this contrast of our peak demand with when flow is in our rivers. This is for the Mount Hope River, which is adjacent to the Fenton River, very similar in geology and size and everything. Where is the water used on campus? And this is from a report, Water Conservation Opportunities, which was done for the university, including part of it by Amy Vickers, who will speak to us later. And we can see that there's a wide distribution of the water use on campus. We do very little irrigation, 3%. We do have some agricultural use, and we have a big chunk here for the central plant. That's the cogeneration plant, which is used for both electricity and steam for heating purposes, and uses water, quite a bit of water in fact. domestic residences, domestic academics, dining services, etc. A little bit of process cooling. That's not so much air conditioning for buildings as we have a number of lasers on campus. Those require cooling, continuous cooling. They never shut them off. And we had a lot of those that just had a one-shot bypass cooling system. We now have changed that as one step in order to recycle that water, cool it, and not have that flow. We use, in a year's time, almost 500 million gallons of water. And, but it's an indication of where we can start to try to save on our water system. Okay, the need for the study, increasing enrollments, which I mentioned. The 4 wells on the Fenton, near the Fenton River, are in coarse grain deposits, and they're fairly shallow, 10 to 30 meters in depth, and are very close to the river, as I'll show you. The river, the wells potentially impact the flow in the river. We have a registered amount of use of 844,000 gallons per day, which is about 1.3 CFS, cubic feet per second. The 7-day, 10-year low flow is about 0.7, or less than an amount. So we have a problem if the river is supplying the groundwater. And the river has been reported to be dry down gradient of the wells back in '66, while maintaining flow coming upstream of the well field. So there's a potential problem there. Our main objectives were to look at the interaction of groundwater and stream flow, and to assess the impact of pumping on the flow in the river, and assess the potential impact of potential flow reductions on the aquatic, namely the fish habitat and fish in the streams. The other major objective was to develop some management alternatives to protect river flows. If we just look briefly at how groundwater systems work in this part of the country in particular, although I don't show here alluvial deposits, the red line represents where the water table would be without pumping, typically. And water's recharged up here, it flows towards the stream, and we have a gaining stream with flow towards the stream from the uplands. With pumping, we draw down the water table. We can then reverse the gradient, reverse the direction of flow, rather than from the uplands to the stream, to be from the stream towards the well. And that's always a danger of reducing flow in the river, and has some water quality implications also. The Fenton River, shown in pink here, above the well field is about 20 square miles. The entire watershed drains to Mansfield Hollow Lake down here, is about 34 square miles. Our hydrology, we get about 46 inches of precip. Half of that, roughly, is runoff. The other half has to go out as evapotranspiration, or ET. It would appear that we have a lot of water. And compared to the west, where they're getting 20 inches of rain, and ET potential is on the order of 60, 80 inches, you know. So here we have a wet climate. But we still have problems. We still have potential for problems. This is the Fenton River near the well field. Very nice river. It's got trout in it, stocked by the Connecticut DEP. This is under kind of normal flow conditions. This is under a lower flow during I think it's 2002. One of my students out there at the time, and we're taking some, just seeing what's there at the time. So you can see it can get low, but it's still got water in it. The study area, and I want to spend just a minute here. Oops, sorry. This is the Storrs campus over here, Horse Barn Hill. The pipe from the well field comes along this white strip there. We have 4 wells along the Fenton River, which is flowing from upper to lower. We have well A, we have well B, we have well C, and down in this vicinity we have well D. These are, as I mentioned, fairly shallow wells. I would like to point out, I'll be referring to Old Turnpike Road. It's this old road up there where it's the head end of our study. And all of the land on this side of the river, by the way, is university land until you get down in this area. We have monitoring wells, either in red or green, and I'll be referring to those later also. And we're located, as I indicated, up here in the northeast corner of Connecticut. The field investigations took place during 2003-2005. Originally, we were going to do it just through 2004, but it was a wet year. Hydrology, we looked at stream discharge and using weirs, flumes. ADCP is acoustic Doppler current profiler. We looked at stream and groundwater levels. We looked at stream bed conductance. We had a geologist and geophysical person from our faculty do some seismic and ground penetrating radar. And we took some geologic cores to look at the type of material in these alluvial deposits around in the valley there. The fisheries consisted of fish surveys, extensive fish surveys, and extensive surveys on available habitat for different species at different flows in the river. What area of the river were the fish of different species using? And this is summer 2004. It turned out to be a very wet year. There's a rule, a law in hydrology that if you're doing a low flow study, you get high flow. If you're doing a high flow study, you get low flow. So this held true in this case. But then 2005, we did get a severe drought. And here we have the flow in the river, very low. August 11th, August 26th, August 8th, and September 8th as we go from Old Turnpike on through the well field here. If you look at this September 8th, you say, oh, it's close to zero. You'd be very accurate there. This is the good and the bad and ugly, I guess you could call it. The normal flow in that section of the river in September 2005. It was dry. We talk about drying up rivers. This is really drying up a river. There's no pools, there's no water left for fish or other organisms to congregate in. So I'll show you why this occurred, but it completely dried up that section of the river. Going back to our study area, our inspection revealed that the river was completely dry from about that point down through the well field past well B, past well A, down to a point below well A. It's about 600 meters that were completely dry in the river. Okay, and there were fish kills, and we suddenly, the university people suddenly agreed there was potential impact from the pumping wells. They'd actually been some people have been telling them differently, but finally convinced them that yes, there is a potential problem here. And so we became the poster child for the bad guys here and what not to do as far as drying up the river. But it really raises the point that at least on these sizes of small third-order type streams in Connecticut, you can affect surface flow, stream flow, by pumping. So there's a direct connection between groundwater and surface water. If anyone's in doubt about that, well, we can talk further, but it really is the case here. We don't have those extensive Midwestern aquifers, the Ogallala, the Jordan, and all those in the Midwest. But we did have severe drought conditions. This is the average rainfall in that area. 1966 was thought to be the one of the driest on record, or was one of the driest, but it still was above what we got. The red dashed is at the agronomy farm about 3 miles from the well field. At the well field itself, where we had a gauge, we did not receive any rain during August or July and August of that year. So it was very dry. We did find, as just a sidelight here, the amount of rainfall falling directly on the well field area actually has a significant contribution to the groundwater supply there. So, just threw this in. We also did a bunch of other hydrology associated with this. These are recession curves. We did a master recession curve. And I just point out that it falls at a rapid rate from about 20 CFS down to 6 CFS. At that point, there's a break in the curve, and from 6 down to 3 or so at a much slower rate. And that's important when we want to assess what time frame do we have when we reach a certain flow, there's no rainfall predicted, that before we reach some critical levels. And it turns out that 6 and 3 are critical levels. Whether the 6, and it's based not on this, but on the fisheries aspect. So, some summary of the hydrologic assessment here. I didn't really go into this about the flow duration curves, but we did find that the flow rate of less than 6 CFS is about 1 out of 2 years on average, and that's important for this university to do some planning. The estimated frequency of flow less than 3 CFS is about 1 out of 4 to 5 years on average. Again, something they can use in planning and managing their system. The expected recession times, it takes about 6 days to go down, if you're at 20 CFS, down to 6.5, 8 days from 6.5 to 3. So it gives you some idea of the timing involved in, again, for no rainfall conditions at those low flows. Okay, the fish. And this is actually one of the more labor-intensive parts of the study. We looked at 4 species, brook, brown, fallfish, and tessellated darter. Of these, the brown is introduced, the others are native species, typical of these rivers. But they've adapted to the amount of flow in these rivers, in this amount of water, in this ecosystem, and the seasonality of that. I was going to point out when I showed that dry riverbed, I think we passed that threshold of peak water there on use. We went over the top there. In this, just give a little background here. We did habitat suitability criteria, measured a whole bunch of parameters: depth, velocity, substrate, cover, etc., and related those to how the fish were using that portion of the river where we were measuring those variables. And we then used that in a hydraulic channel structure model, PHAB-SIM, if you're familiar with that, to get at the amount of usable area by species for a particular discharge. So if you give us a discharge at a certain point in the river, we can say, is that conducive, or how good is that for a selected species? It won't necessarily be the same for different species, as I'll show. So we then take that information and we put it into a time series. Again, these are for amount of usable area as the flow rate would vary day by day throughout time here. And again, these are for 2 different species. One may want high flow, one may not like high flow. We also can then use that to get at the amount of time that we have a certain suitable habitat available for the fish. So here we can do exceedance curves based on that. A couple just results, example results of the study. Here I mentioned tessellated darters. They like the peak habitat comes about 20 CFS. They like that shallow rapid flow over rapids, ripples area. The other 3 peaked around 50 CFS or a little less. Very similar in their habitat preferences for there. So that was helpful. We then take that information, and as I mentioned, we do these curves, which are the durational curves, and they're called cut curves or continuous under threshold curves. And I have to acknowledge my cohort, Piotr Potashevitz, for that work, he and Rick Jacobson. And those are very helpful because we can use then those along with the change in flow to get at when, as we are pumping and we're reducing flow in the river, what is the change in discharge, available habitat, and the duration of which we're stressing the fish over a longer period of time. So these are some flow and habitat suitability curves for the river. And certainly as we get down in here, they're stressed out. But if we lengthen that period in which they're stressed, we are adding to the ecological impact from our pumping activity. Okay? The groundwater part is very interesting. We did this seismic work and stuff and did pump tests, etc. We actually modeled, the main thing was the model, the mod flow model, if you're familiar with that. Some of people may be. And then after we calibrated this model, we looked at the predictions of impacts for pumping alternatives. The idea of being able to minimize impacts of that well field on the habitat or in the flow and then the habitat in the river. So just a little bit of this is our the valley in here, which is stratified drift, which provides most of the water, but there are contributions from these other areas of till and thick till. And again, the university campus is up here. The results of the ground penetrating radar and seismic were very helpful. I'd highly recommend that for somebody doing one of these studies. And that we did these, Dr. Lanbo Liu did with his students some of the seismic work. It really helped us to assess the depth to bedrock, depth to certain layers, depth to even water tables, and it was very helpful in calibrating, setting up and calibrating the mod flow model. We did pump tests, and this is just a calibration thing, if you will, for picked out this area. This is when, I throw this in here because this is when well B comes on, and it's not pumping at a steady rate here, then it goes off. You can see the response in those monitoring wells immediately. The water level starts dropping, then pumps go off, comes back up, and then goes back on, goes down. This monitoring well was farther away, didn't seem to have the impact. You may have also had a restricting layer in there someplace. So the pump tests helped us immensely in calibrating and setting up the model. After we had done that, we got the model calibrated, and we thought we think we did a very good job in getting the model calibrated. We tested it. This is for one day, again from Ron's study, some data he had for wells where the pump's off versus pumps on. And we can see, even though these are small numbers over here, 0 to about 0.5, we see that we can have a big impact. These upward trends as we go again from Old Turnpike through the well field and down to Gurleyville Road are due to inflow from some tributaries that come in below the well field. We then tested several scenarios, and I'm just, there was many more than this, but I want to highlight 3 groups here of our tests. One, the first group is excuse me, pumping spread over more hours of the day, but at the same total amount. The second group is excuse me, where we started reducing the total pumping, so we were able to compare 3, 4, 5, and 6. And then the last group is where we moved well A, and I'll show you a diagram of that in a minute. But again, we could assess the impact. This is with no pumping, and we could determine, in the bottom one here is with the scenario 1 is the maximum rate in shortest time. This one is where we moved well A away from the river. Okay? So we were able to assess the impacts of different management alternatives and give recommendations. This is, again, the well field, and well A here is if we moved it, in this case, 250 feet to A prime, a double prime is kind of halfway between well D and well A in the deepest part of the aquifer. One of the things we found through the geophysical work is that the deepest part of the aquifer is over in here. The river's running over here along fairly shallow bedrock. And so we're missing the biggest storage of water in the deeper part of the alluvial deposits there. If we looked at this, we can see that there's minor improvement as we go from alternative 1 to 3, where we're just spreading out the amount we're pumping, total same amount but over a longer time. Very little improvement. It's when we start to reduce the amount we're taking that we get the biggest reduction in the impact on the stream. And this is in terms of the stream loss in CFS. The second biggest impact was where we're moving well A to a different location. In this case, that's approximately 1,000 feet away. We get a big reduction again in the effect on the stream in that regard. Okay? So our major recommendations coming out of the study were, there's some more than this, but these are the major ones. Install a stream gauge at Old Turnpike Road, and the university has done this. It's a USGS gauge now. You can go to it on the web and download what it is immediately, and they monitor this on a daily basis. We start reducing pumping when the flow at Old Turnpike Road reaches 6 CFS, and we go in steps. Here is shown gradually reducing that, and then when it reaches 3 CFS at Old Turnpike, we stop pumping that well field. Fortunately, we have the Willimantic well field, but it puts more stress on that well field, and we're now doing a study on the Willimantic well field to determine. It's a much larger river, but we do pump at a higher rate than that. And we recommend that we replace well A at a new location. The report is available at the Connecticut IWR website, so ctiwr.uconn.edu, if anyone wants to read a 200-page report. A lot more details. Okay, I want to go back then to, as long as I got time here, and to what has happened since 2005. And to its credit, I think the university has done really grabbed the issue and is trying to make amends to correct the problem, because they finally realized they have a problem. Okay, again, this is the water use, and as you see, it goes down here from 2005 to 2007. And I would indicate that 2008 it also continued to drop by another average of 22,000 gallons per day. This is through a number of things: better operation of the system, and optimizing some of the pumps, things like that. Leak detection. They've done some leak detection before. They made improvements to the buildings and infrastructures. They installed meters in all the major buildings and some of the residences, things like that. And they have done an educational campaign to heighten awareness and to educate students and staff, faculty, about the need to conserve water. These include, and some of this is based on the report done by Amy and other of her colleagues who had written a report in, I think, 2007. Low flow devices, typical. They've been doing that in all the new dorms. We've gone back and retrofitted many of the major uses. There's not some buildings yet, the old, say an office building that may not have it yet. Flow restrictions in the dining halls, some irrigation controls for the irrigation of athletic fields that we do irrigate. Rainwater harvesting is perhaps relatively minor yet, but it's on the board here as a potential source of water. As I mentioned earlier, the air-cooled and closed-loop cooling systems have been installed. Steam system repair and replacement is a big one there. If you remember that pie chart, the central plant there uses a lot of water. And then some in our ag operation, the high-pressure water brooms and poultry barn retrofit, some of those. I saw there's a whole list of these things and a cost-effectiveness thing. And we have quite a few animals on campus, even lab animals, rats, mice, that type of thing. For a minimum amount of money, like $1,000, we can save 5 million gallons a year. So just by the way they change the watering and the cleaning of some of those cages and things like that. So there's really some opportunities here that are being undertaken. And just as an example here, this is part of the outreach thing, but we do follow a LEED Silver policy for all new construction, and they include, of course, the low-flow devices and laundering included that, and for putting in native and adaptive landscaping, so we don't have to water even some of our gardens and things like that. Our Office of Environmental Policy has gotten involved, and with an outreach effort involving a lot of students. There's something called Eco-Husky that I'll talk about in a minute. But they've come up with this Stop the Drop, and we have signs in bathrooms in different places where if you find a leak in a faucet, toilet, report it. And they've got the facilities people responding quickly to fix those leaky facilities. They also have, one of the things they did was try to educate students, and they had a dorm contest, one dorm against another, in which they tried to see who could conserve the most energy and water. And the results here, I don't know what happened with this dorm, whether they used more water, but most of them reduced their water somewhat, and the maximum was 10%. So that we did find that back in 2005 when they put out alerts and warnings about water conservation, some areas, some dorms, water use actually increased. And it was kind of this, you're not going to tell me how long I'm going to take a shower type of thing. So, but with education, I think that's coming around, and we're starting to see some results of efforts there. Okay, some next steps. University's exploring. As I mentioned, they're doing a study on the Willimantic River. They're studying the potential for wastewater reuse or makeup water in the cogen plant. This amounts to, could be as high as 400,000 gallons per day, which is really a major use. And when you think about it, water conservation can take us a certain distance, a certain ways. In the end, I think, as Peter was saying, alluded to, we have to think about water reuse. And here, this water reuse in one instance can save almost twice what we have saved through conservation efforts, so on the average. So that's the next step, although it's very expensive. We're talking tens of millions of dollars here potentially. But the other thing about this is, if a university doesn't conserve water and have water reuse, they're going to be limited for the growth in the future. They're either going to have to bring in, find a new source, which are tens of miles away, so that's very costly to bring in also. So that's kind of where the water reuse is one area they're really seriously looking at and are doing studies on. We're looking at, of course, continued use of low-flow devices in buildings and our landscaping policies. And we're going to continue educating students and staff about the need to conserve water. I think that's, I'd like to acknowledge this study involved a large number of people, and I would just highlight Ross Bagsaglu, Fred Ogden, and Piotr Petashevitz, and Rick Jacobs in there. But it's involved cooperation from many parts of the university also. With that, I'll take questions, but I'd point out how quickly things can change. On the left is where the river was dry in September of 2005. Approximately 5-6 weeks later, it was the highest flow on record. Okay? So that's hydrology.